Hey guys, welcome to the video. So in this video I want to speculate with you on an interesting physics idea, which may not be real physics, by the way, nothing rigorous or anything, nothing proven or anything, not kind of it's not like any real research or any established physics, but I just want to speculate with you on this all the same. So I'm trying to connect back to one of my previous ideas, like very recent but still important, with a realization I had just in the last week maybe. So it's about, if you guys, some of you guys know probably that I posted a report, kind of like an article, a speculative article, in which I tried to connect quantum mechanics with statistical mechanics, statistical physics. Now it was mostly speculative again, and I'm not claiming that I did real physics in that particular article. Let's be very blunt from the very beginning. But yeah, there the argument was that I tried to draw some possible potential connection between entropy, the concept of entropy in statistical physics, and more particularly the second law of thermodynamics, that the entropy increases in the universe. So I try to connect that with quantum uncertainty, the Heisenberg's uncertainty relation, uncertainty principle in quantum physics. And I'm not the first to do this. There are more rigorous theories as well, but I have tried to take a slightly different approach, which is very simple, very speculative, very qualitative, not quantitative yet. So yeah, and the basic argument, just to give you a quick recap, because this will be relevant for the next part of the video, the main part of this video in fact, is that I kind of argued that since there is the uncertainty principle, if you know even basic statistical physics, the classical statmech I'm talking about, you may know that we divide the phase space we have as phase space, right? The position versus the velocity or the momentum, whichever you prefer. So we divide the phase space into phase cells, which are elementary volumes of finite volume, and this is to differentiate between different microstates. So each point on the phase space is essentially a microstate. If you know the position and momentum of a particle at any given time, then you technically know its complete state. That's the microstate. Now and this is kind of, you can directly, this is actually rigorous, the thing which I'm saying just now. This is actually directly, this can be linked with the uncertainty principle, although historically things are not just in a chronological order maybe, but this is a direct consequence, because on one axis you're plotting position, on the other axis you're plotting momentum or velocity, whatever, mass times velocity is momentum. So if you have to divide into elementary volumes, that is precisely because you cannot specify the position and momentum of a single particle at the same time simultaneously. You cannot specify both accurately. That is the uncertainty principle, right? So that's why there is some uncertainty in your position, some error in the position along the position axis, delta x, and the same along the momentum axis, delta px. It's the momentum in the same direction, mind you. So yeah, now where does entropy come into the picture? So entropy, you can think of entropy roughly as if there are more number of microstates for a given macrostate. What do I mean by microstate and macrostate? Again, just to give a very basic idea, let's say you have a box with 5 balls in it, and they are differently colored. Let's say one ball is red, one ball is green, and so on. So your macrostate could be that the number of balls could be a macrostate because it's 5. But let's say within the box you have 5 partitions marked 1, 2, 3, 4, 5, and you can shuffle the balls within those partitions, right? You can keep the red ball in partition 1, the green ball in partition 2, or do the other way around, and there are many different combinations. So the statistical physics definition of entropy is just that the more the number of microstates, the more the entropy. So it's not a directly proportional relation, but I don't want to go into the mathematics, the exact equation, just the idea. So you could have 5 balls in the overall box. For the same macrostate, you could have many possible microstates, because you could arrange those 5 balls in many different ways within those small compartments within the box. So now think of so all those different possible combinations without changing the number of balls. The number of balls is still 5, so you're in still the same macrostate. Macroscopically, it's similar, it's identical. So those are the different microstates corresponding to the given macrostate. And on the phase space, there are different points on the phase space actually, just to give an idea. So yeah, now the idea was that maybe we could kind of use this argument that since there is uncertainty principle, since there is uncertainty in the position of momentum, the phase space is the phase space needs to be divided into phase cells of elementary volumes, finite elementary volumes, and because of this, there if I put it in a very rough way, very like kind of speculative way, just don't judge me on the rigor here. It's just a speculative video. Just I told you in the very beginning. So then technically there is wiggle room for entropy to increase, because if you did not divide the phase space into phase cells, if you could distinguish every point on the phase space from every other point, technically you would have infinite number of microstates. Like even if there are 2 points which are infinitesimally close, but they would still correspond to different microstates in that case. So then your number of microstates is already infinite. Now again, there are some mathematical arguments which will contradict what I'm saying here, because infinite is a vague term. Even infinities can be countable infinite, uncountable infinite, and especially here we're talking about physics, not about mathematics. So infinite number of microstates, I need to specify exactly what I mean by that. And again, this is just a kind of thought experiment. It's not real physics, but yeah, if the Planck's constant would have been 0, then this would be true, because in that case the uncertainty principle delta x delta px, which is greater than or equal to h bar over 2, right? So in that case, delta x delta px, the product of the uncertainties in position and momentum could be 0, would have allowed, like we could have allowed it to be 0 if the Planck's constant was 0, but it's not. It's a very small number, but it's non-zero, and it's a very very important, right? So that is the basic idea. And so since the Planck's constant is non-zero, what we're saying is that there is some room for entropy to increase. Now it's very clearly written in the report. I'll drop the link in the description, by the way, if any of you are interested. So we are not claiming that entropy increases because of quantum uncertainty principle. That's not true. That doesn't sound true. And even if, like, that's not even falsifiable. If I claim that there is no way to prove it using physics or using any rigorous method. So why does entropy increase in the universe? That's an age-old question, and that's a very deep question. We don't know the answer. Even Boltzmann, the father of statistical physics, he wrestled with it a lot. And you can check out Boltzmann's past hypothesis. I don't know if you know about the past hypothesis, but it was a very interesting argument, kind of like a thought experiment which verges between physics and philosophy. But then Boltzmann went on to describe something which may have heard, called Boltzmann brain. So basically, we don't understand why the universe began in a low entropy state, but the only way to explain why entropy increases in the universe is to assume that we began in a very low entropy, very unlikely state, right? Because high entropy state would be more likely. And if you think about it, statistically, we don't have an answer. We cannot explain why the entropy increases in the universe, because the second law of thermodynamics is just it's not really a law which you can derive analytically. It's kind of like a statistical law. So it's in our universe, entropy increases almost certainly, but you cannot treat this as I mean you cannot explain exactly from first principles why it is the case. And that is why Boltzmann thought about this, and he was led to these absurd conclusions about statistically it's more likely that the universe is just a single brain, Boltzmann brain. I discussed Boltzmann brain in one of my previous videos. If I remember, when uploading the video to YouTube, I'll drop the link of that video as well in the description. You can check it out. I don't want to go deep into Boltzmann brain in this particular video, but yeah. So now my personal thought is that the reason entropy increases in the universe has got more to do with cosmology. I mean, the precise initial conditions in the early universe near the Big Bang. Again, we don't know if the Big Bang theory is ultimate, or whether Big Bang was indeed the beginning of time. There are some models in cyclic cosmology and stuff, which I'm not very much aware of. But yeah, I mean, I get to hear about this a lot from my colleagues who are working in cosmology, and it's pretty interesting, but okay, not my cup of tea, so maybe I'll not make any comments on that. But yeah, so the thing is that we don't know why, and it's no good pretending that we do. But what we're saying is that maybe if the uncertainty principle was not true, I mean, if there was no uncertainty in quantum mechanics in the microscopic world, then maybe entropy could not have increased, even if the other conditions, the so-called cosmological conditions, if I put it that way. Actually, it's all very tied together. It's not like we have compartmentalized physics into this and that different branches, but fundamentally everything comes into play. Especially if you think about a state like a Big Bang, which is a very, like, it's a state, high energy state, yet a very tiny state. So quantum mechanics and cosmology, general relativity, everything will come into play. So that's why we don't yet know what happened, but actually we don't understand that actually rigorously. We would need a theory of quantum gravity, the so-called theory of everything, for that. Yeah, so that was the argument. And maybe there is some link between uncertainty and entropy, and uncertainty quantum uncertainty leaves some wiggle room for entropy to increase in our universe. Okay, but now, but that was very hand wavy argument. But now recently, when I was just taking a course in hydrodynamics actually, and I was just suddenly I realized that if you look at Schrodinger's equation in canonical quantum physics, the Schrodinger's equation is just an equation. You just need to know what it does. You don't need to know it rigorously for this particular video at least. So I'll just maybe spare 1 or 2 sentences for my viewers who are not very much mathematically literate about Schrodinger's equation. So it's just an equation which governs the time evolution of something we call the wave function. So wave function is something in quantum physics, in canonical quantum physics at least. It's something which gives you some information about the particle. So from it you can extract the probability about the particle being in this location or that location, like that. So I'll skip the technical details. So let's say I give you the wave function of a particle now, and using Schrodinger's equation you can find out where it will be after some time. So it's basically we're studying the time evolution of the particle using the wave function. The Schrodinger's equation is basically a differential equation, and the solution to this gives you the solution to your psi, the wave function, which is denoted by the symbol psi. Right. So, and if you look at the structure of the Schrodinger's equation, there is a term, the potential term, which is v psi, where v is the potential and psi is the wave function. So for a moment, if we ignore the term, we can ignore the term if we are talking about a free particle, maybe a particle in deep space, no potential wells, it's not experiencing any force, any kind of potential. So that's a free particle. So for that particle, v would be effectively 0. So for such a particle, if you look at Schrodinger's equation, there are just two terms, and in one term we have a Laplacian, which is a double derivative with respect to space, and the other term we have a single like a time derivative, like del psi del t, but it's imaginary time, which is very important to note, because in Schrodinger's equation we have imaginary, like we have the imaginary number I, and it's people who are just starting to learn quantum physics, they find it very difficult, and I get it why, because I is an imaginary number, but Schrodinger's equation gives us something real. I mean, it gives us the outcome of a quantum measurement, which we do on real particle, and of course the outcome is not imaginary. That's why we take the square of the modulus of psi if we want to calculate the actual probability density, because the actual probability density cannot be imaginary. But a lot of people have difficulty imagining why should there be an I in an equation which describes something real, because I is an imaginary number. It's just I don't know, like the I is a very deep concept. I don't know how it is perceived by, but it's usually not just a mathematical trick. There is something deep in it, and it's a very standard trick all across physics that we have. We have this I in our equations, but we somehow get rid of it when we are giving the final result, which obviously cannot contain an I. In fact, just to give a historical remark, Schrodinger actually himself was uncomfortable with this, and he tried to do a fourth order differential equation. He tried to get rid of the I, but he couldn't, because that didn't work out. This I couldn't get rid of it for some mathematical reasons which I cannot go into in this video. To be honest, I myself am not very much aware of this particular thing as well, but yeah, I've heard of it, and I think it's very important, because yeah. So now if you think of, if you replace real time with imaginary time, now this stuff, it's very easy to say, but it's more difficult to actually understand what I'm talking about, right? But okay, for a moment, if you think about, in imaginary time, Schrodinger's equation is just like a diffusion equation. We have a double derivative in space and a single derivative in time, the same form which comes up in diffusion equation, which we study everywhere in physics, in in hydrodynamics, even in electromagnetism. We have this you can think of it as like the diffusion of current. This continuity equation, and continuity equation is not diffusion equation, but no, sorry, that is not diffusion equation, but we get this in heat equation, which governs the diffusion of heat, and we get this in fluid dynamics, in hydrodynamics, and we get this in a lot of places in physics. And this structure is very important: a double derivative in space and a single derivative in time. But the important point which I want to mention in this video is that, so in the heat equation, which is actually a diffusion equation, what is diffusion is actually the temperature. You can think of it, the heat is what is diffusing, or in a way the energy is what is diffusing, because when we talk about the diffusion equation, something must be diffusing, right? So if we think of the Schrodinger's equation, at least the Schrodinger's equation for a free particle, where the V term is 0, so if you want to think of the equation as a diffusion equation, then what is diffusing? You could say, okay, maybe the wave function is diffusing. What is the wave function? The wave function contains some information about the particle, okay, which we can use to calculate the probability density. But can information really diffuse? Because in real time as a whole the probability is conserved. The total, if you look at the total system, the probability is conserved, if information is conserved, unitary. The time evolution of any quantum system, any quantum state is unitary, which is ensured by the Schrodinger's equation itself, mind you. So and I don't know the answer, of course. I don't even know whether this actually makes sense physically to ask, like, to compare Schrodinger's equation with the division equation directly like this, because I told you there is this problem of imaginary time. But if we for a moment just try to think about what is actually diffusing, I don't know the answer, of course, but I think this could, I think uncertainty principle could play a role here, because okay, just to give you a very like a qualitative kind of let's say a reminder. To derive Schrodinger's equation, you use de Broglie's relation. Again, Schrodinger's equation cannot be derived analytically in that sense. We can only show that it's true for some very specific cases, but it somehow works for all cases. So it's kind of like a postulate. You cannot derive it from first principles. Newton's second law is a postulate in Newtonian mechanics. So Newton didn't derive it analytically from first principles. The Schrodinger's equation is just like the law of motion in quantum mechanics, just like Newton's second law, the counterpart of that law in quantum physics. So you cannot derive the law, but yeah, when you try to show it for the special cases, you use h over p is lambda, which is de Broglie's relation, and that subtly hints at the uncertainty principle, because h is a constant. So if h over p is lambda, then h equals p times lambda, where p is the momentum and lambda is the wavelength. So wavelength is related to resolution, like if you are trying to like resolution, wavelength. So that we can link it with the position, the uncertainty in position, delta x, and p is the momentum, so you can link it with the delta p. At least dimensionally you see that, of course dimensionally it will definitely be true. There is no reason to expect otherwise, but you can think of it. So quantum physics is a unified framework, quantum mechanics. So of course Schrodinger's equation, uncertainty principle, they are all, they obey each other, of course. Now my idea was like, if I tried to this realization I had about Schrodinger's equation being a diffusion equation, my idea was, could we somehow link this to what I have written in that article, like that speculative article of mine, whatever I discussed so far, like phase space, phase cell, entropy, uncertainty, and all this stuff. Because again, if the uncertainty principle was not true, then in a way, if I put it in a very speculative kind of way, again, it's not in a very in a way, information could not have flowed, let's say flown. Like if you think of information as a fluid, like information is not really the fluid. You can think about the phases, the probability, amplitude, some phases of information to be, we could think that they are flowing between different regions in space, because overall the information must be conserved, as we know. But you can have like you can have like the probability, overall probability is conserved, of course, but you get the particles at different positions if you do measurements at subsequent measurements in different times. So that means there is some, you could think of it, the probability is flowing in a way. We actually have the continuity equation in fluid mechanics, in a lot of other places in physics. We have such a similar equation in quantum mechanics also. It's the continuity of, if you think about it, the probability current, just to draw an analogy, So if we, that's all I actually wanted to share in this video. Like, so if we think that the uncertainty principle is uncertainty is what keeps diffusion alive, and what is diffusing, well, we don't know. That would be the most honest answer, but maybe something like the information related to the probability. In imaginary time, of course, that's true. In imaginary time, mathematically, you can see that indeed this is what is diffusing. In real time, if you want to maybe rotate it by 90 degrees, and in real time, imaginary to real means you rotate the complex plane by 90 degrees. But what does it mean here physically? Because that's the mathematical definition. We don't know. So yeah, but I think it would be I wanted to do. I talked a lot about this, about all this stuff in this video, because I think it's a very good idea to try to relate between different, like for instance, this insight that Schrodinger's equation is just like the division equation. It's not new. You can, I bet there are some textbooks at least which mention this, and there are a lot of people who have thought about it. So I'm not the first one, of course, but it's still often overlooked in classrooms, in courses, in discussions. Like, it's often overlooked. Right now we are learning the heat equation, or maybe the diffusion equation in some other context. So why should we talk about Schrodinger's equation now? We should, because I have personally believed it's always important to draw connections between different, not just about physics, even in life, whatever subject you are into, whatever you are studying or not, it's always a good idea to do that. That way you can see the bigger picture, you can see the underlying patterns. Because at the end of the day, what I personally believe, although this might sound a little bit too idealistic, but what I personally believe is that physics is a coherent framework. So there are a lot of patches which we like, there are a lot of questions which are unanswered today. We don't know this, we don't know that, this is not compatible with that, this theory, like for instance quantum mechanics, the tension between quantum mechanics and gravity. But I personally believe it is. And maybe in the future, I don't know, but I'm not saying we will find a theory of everything, or anything like that, but I definitely believe there is some coherence underlying the different branches of physics, some logical continuity and flow. And so it's a good idea to think about these kind of things, to think about, try to think about, for instance, when doing hydrodynamics, if you just another example which came to my mind, if you do Euler's equation, you use the tensor, I mean the stress momentum tensor, something like this. So it's, again, in fluid flow, actually you use the division equation a lot. The momentum is diffusing in a transverse, especially in the Navier-Stokes equation, just when you're in the boundary layer, right, just near any obstacle in the fluid. So when Euler's equation no longer works, when viscosity comes into play and things are way more complicated. So anyway, so in fluid dynamics, we for instance we have this tensor which simply says it's nothing, just what the equation is actually telling you is that it's kind of like a conservation law. So again, this relates to a very fundamental idea in physics, which is Noether's theorem, which says that which is a correspondence between a symmetry and a conservation law. So for instance, I made a couple of videos previously, I believe, about this, but so I'll not discuss it in detail. But yeah, for instance, the law of conservation of energy can be linked to time symmetry. The law of conservation of linear momentum can be linked to translational symmetry. So the symmetries are very useful, very important tools in physics. Symmetry means, for instance, and by symmetry, usually what the high school students, they have, to them symmetry is like geometric symmetry. If you have a shape which is not that, here symmetry could be a lot of things. For instance, if I say that if I do a physics experiment right here, right now, and if I do the same experiment under the same conditions 2 days later, in principle I should get the same result, and that is a time symmetry, which is, in simple terms, the laws of physics do not change with time. So it could even be symmetry of laws, not just geometrical symmetry. So basically the example I was giving in hydrodynamics was about the symmetry. This is a symmetry of, you could think of it as a kind of symmetry, because this equation is actually technically a momentum conservation equation, but you see, there's a non-zero term. So it's actually I forgot the details, and I don't want to bore you with the mathematics as in any case, but this is true only locally. But if you look at a fluid, there are a lot of complex stuff that's going on, so it's not really, momentum is not really conserved in that sense. For instance, I can give you another example, and this is why I brought up this example, because this could be a very good way to think, to link, not physically, like not rigorously, but to link the approaches or the concepts in hydrodynamics with general relativity. So in general relativity, we have something like, first of all, is energy conserved? It's not actually. In local time scales and length scales, it's usually conserved, yeah, definitely. But for instance, if you look at a photon which was emitted just after the Big Bang, like maybe billions of years from now, and if you look at the same photon now, would you expect it to have the same energy? Of course not, because the photon has moved through the universe, and it has lost, it has radiated its, that is a very common misconception. People say that through time the photon has radiated its energy, and its energy has dissipated into the surroundings, so overall energy is still conserved, but the individual energy of the photon is less. It's not that. It's wrong, it's incorrect to say that the photon has dissipated energy. It's more correct to say that the universe is expanding. Think about this, the universe is not a static, the universe is itself expanding. Then there is curvatures and stuff in general relativity. So since the universe is expanding, the photon actually, the more appropriate way to look about it, to think of the situation, is that due to the expansion of the universe, the wavelength of the photon has increased, kind of. So it's not because the photon has emitted energy, has lost energy to its surroundings. No, due to the expansion of the universe, the wavelength of the photon has increased, and the photon is definitely at a lower energy now than it was billions of years ago. So where has the energy gone? It would be incorrect to say that the energy has gone to its surroundings. No, because again, like I told you, the universe is expanding. The answer to that is that at astronomical timescales, like at timescales of let's say billions of years, or the length scales of the universe, the law of conservation of energy no longer holds. And if you look at the history of development of general relativity, Einstein, Noether, and all, you can look it out. I actually read this somewhere. Anyway, so I don't remember the source exactly, otherwise I would have dropped that too in the description. but you can definitely read this. So the basic idea is that if you the energy is not conserved, because we shouldn't even expect energy to be conserved, because the law of conservation of energy is linked to time symmetry. And in general relativity, especially at the time scales we are looking at, for instance the example with the universe expanding and like billions of, time symmetry does not hold, because things have changed from the big bang to today. You cannot expect, like it's not really at this scale. Time symmetry does not absolutely hold, so we shouldn't even expect energy to remain conserved. So simply energy is not conserved. It's not like, okay, the photon lost energy to its surroundings or this, no, not that kind of thing. And we get similar situations in all of physics. Hydrodynamics one, I gave it example because it came up to my mind. I recently did this, but again I forgot the mathematical details. So in any kind of this kind of equation, if you have a non-zero right hand side, which means you have some divergence, some non-zero divergence and stuff, then of course things are no longer conserved. So you can think of it as a source versus sink mechanism. So if you have a source of could be anything, source of particles, source of disturbance and stuff, then things are no longer conserved. And if you have a sink is kind of like an anti-source. It's the same thing. But I think it's very important to think about this in this way, because it acts as because this is something which we use in all different branches of physics. And the example with general theory of relativity and the photon, I think it's a very good example, because it's something which most students get wrong. They have they have a misconception. So if you just ask them, is energy conserved globally, they would almost always say yes. Well, it's not true. Depends on, so in any case, whatever you're studying, it always depends on the context, on the length scale, on the time scale, on the energy scales. For instance, for people like us who are working in statistical physics, or not statistical physics, we use statistical physics a lot, but we're working on understanding biological systems. So for the length scales which we work in, of course energy is conserved. I mean, we don't need to worry about the kind of non-conservation I illustrated with the photon example. That is not something we need to worry about. But for someone who is doing cosmology, general relativity, these questions would be very much relevant. So yeah, I think this is enough. That's all I wanted to discuss in this video. And I think this was kind of like this video was kind of like longer than necessary, but I hope I gave you some, I don't know, some good idea, or some good ideas to ponder, to question, to think. I mean, this may not be real physics. This is maybe probably not rigorously real physics, but still this is something you can think about, and thinking about this will help you in your understanding. And maybe if you're lucky, you can also find spot some more connections. It's fun, isn't it? So yeah, and thanks for watching. I'll drop the link of the article I mentioned in the description. And as a closing note, I think you can definitely check out the article, because even apart from the technical, like the hypothesis which I told you, near the end there are some appendices which I've added in the article, in which I have discussed in very layman friendly language, in which I've discussed some other, like some concepts, some illustrations. For instance, in the appendix 1, I have used a lot of examples, like for instance rubber band, polymers, gas particles, a lot of examples to show how the interplay between three parameters, energy, entropy and symmetry. So try to illustrate this, because studying the interplay between these three parameters is a very good way to study how complex systems behave, in my experience, in my opinion. You can read it for yourself anyway. And the second and the last appendix is about the black hole information paradox. So again, this is something which I have talked about a lot in my previous videos, even in my writings. But the reason I think this is very relevant is that it's probably the best example of what happens when we try to fuse together two theories that are incompatible. So black hole information paradox is kind of, we're trying to fuse quantum, the predictions of quantum theory, like for instance virtual particles in the vacuum, with the predictions of gravity, general relativity, for instance black holes, and we get something we cannot explain, a paradox, the information loss paradox. So yeah, it's kind of like very layman friendly article. I've just written it kind of, it's an article, it's not a paper, so it's written for, so that anyone can understand. And that's the point. I personally believe, instead of just unnecessarily like making things more technical just to show off and show authority, I think it's much more important to, this science communication, so that even everyone can take something from the article, whether they're high school students or just undergraduates, or even if they're more experienced professionals. So yeah, I hope you like the video, and I would like to know your thoughts in the comments. And yeah, sorry for making it extra long and maybe wasting some of your time, but this topic is definitely interesting. Thank you. Thanks for watching.